So it's 1:06, so we're ready to start. We continue our workshop, and my name is Simone Gasparinetti. I am assistant professor at Chalmers, and I have children in the background. I hope it works fine. So I would like to welcome Marina Kudra as the first speaker of this session. She is from Chalmers too, and she will speak about preparing Wigner-negative states with displacement-SNAP blocks. So Marina, please go ahead. And all the speakers have, I remind you, 15 minutes plus 5 minutes questions. So I will text you if you are exceeding your time. Please, Marina, welcome.
Yeah, thank you, Simone. So as Simone said, I'm from Chalmers and I'm the part of WACQT. And my supervisors are Per Delsing and Simone Gasparinetti. And remember these names, like in 2 slides, it will be important. So I've been trying to generate non-classical states for continuous variable quantum computation using these SNAP and displacement blocks. And I wanted to give a little bit of motivation, but we had Jeff, who already presented his very nice paper on autonomous quantum error correction. And then he also mentioned the one that broke even, also the Nature paper from 2016. So why are these systems so good if you want to do error correction? So first you have this long-lived storage mode, and then you have this dominant source of error, which is this single photon loss. And on top of that, you have freedom to encode your state. So if you choose that wisely, that helps you a lot. It's somehow hardware efficient. And here you can see these cat codes, and in this case as well, it's almost a cat that's encoded, but you are in principle free to choose whichever code you like. So let's say you would like to do something like this, and then it's maybe wise to make like a checklist, everything you need before you can do this. And maybe you want to do it, but maybe your supervisors really want you to do this. So whichever one is the case. So first, it would be nice that you have this long-lived 3D cavity that will make your life a bit easier. And then you should integrate a transmon, and these checks are like, I managed to do these parts. And after this, you have to create this non-classical state of your choice, and the higher the fidelity, the better. And then there is just one more step, now you just keep it from decohering, dephasing. You have to protect it from Kerr evolution, and then whatever you are doing, whether it is this active way of measuring your syndrome of your error, or if you're just doing it autonomously, you still have to make sure that you are not making it much worse than it was. So just one slide about these 3D cavities. So they are machined blocks of aluminium. They have this stub geometry. And I spent quite some time making sure that I can make them reproducibly with high quality factor. So this is directly proportional to how long your photons will live. So the main message of that paper was that if you machine your cavities, they already have quite, let's say, high quality factors, but they're spread. The spread is big. Then you edge them to remove the surface induced any sort of imperfections from machining, and they get better, and the spread is smaller. And then you just anneal them in a furnace, and they get a bit better again, but now they're really reproducibly quite close to 100 million internal Q, which translates to few milliseconds, depending on your on the frequency of the resonance frequency of your cavity. So good, you have the cavity. Now there is a transmon. It's a chip which you will, you know, slide into your cavity. If we zoom in a little bit, you can represent these three modes as a circuit, and then your readout resonator is this linear mode at 7.3 gigahertz in my case. The qubit is the nonlinear mode, our ancilla, that's going to allow us to do something that's not a coherent state. My qubit currently is about 10 microseconds. It's both T1 and T2, and sitting at 6 gigahertz. And now there is this cavity, which is, in my case, 300 microseconds, sitting at 4.5 gigahertz. And it has a bit of this Kerr inherited from the qubit. So the important parameter is this chi, this dispersive shift between the cavity and the qubit. And that one should be large enough to allow you to do these SNAP gates. So you can look at this system as a circuit, but you could also write down a Hamiltonian. And then there are these frequencies of the modes, the dispersive shifts pairwise, and then the Kerr of the cavity and the correction to the dispersive shift between the qubit and the cavity. And if you would like to make these high fidelity states, you better measure all of these parameters as best as you can to be able, to be able to drive your system accordingly. So good. I have a working system. I managed to couple a transmon, and now I chose to create my states by using displacement gates and snap gates. And displacement gates are very simple. They are just a pulse at the cavity frequency that we send to the cavity. And then to probe which display state we created, we send a very long pulse to the qubit, a long pi pulse, and then we change the frequency of this pulse. And that's what you can see here on the x-axis. And then we probe which state the qubit is in. So we have this readout amplitude. And it's a bit upside down. So if the readout amplitude is high, it means that the qubit is in the ground state. And if it's low, it means that it is in the excited state. So this is the picture you would get if you don't drive. If you don't send this displacement pulse. And if you do, you notice that more peaks appear, and they're spaced exactly this chi QC, the dispersive shift. And then you drive a bit harder and more peaks appear, and they start moving to higher average photon numbers. And the very nice thing about this is that we can directly read from the area below this peak what is the probability that we will have this certain Fock number. And if we know that we will get a coherent state, so if we fit these probabilities to have certain peaks, we will know exactly which alpha we are making. So here there is nothing kind of quantum sort of yet. That's where the snap gates come in, and that's what we need a transmon for. So the selective number dependent arbitrary phase gate, if we have some arbitrary state in the cavity, what the snap does is that it will add an arbitrary phase to each Fock state, to each Fock number. So how this works, if you keep the previous picture in mind, and if you want to add some phase phi 0 to the vacuum, you will send a tone that is again very long. It's actually 2 pi pulses again, centered on the frequency phi 0. and the angle of the axis between two pulses will be shifted by this phi0. And if I want to add this phi1, I do exactly the same thing, just at this frequency f1, and so on. So I basically send a comb of frequencies. And the tricky thing here is that these times have to be bigger than 1/chi, sorry, much bigger, so that they selectively drive each of these transitions. And because our qubit doesn't live forever, this will induce quite some amount of error. So instead, you can choose, you know, your optimizer of choice. And for me, this was this company owned optimizer called Boulder Opal. And then you just send a wiggly pulse to the qubit. And now instead of, let's say, this taking some 4 microseconds, now it's taking about 500 nanoseconds. And here just an FFT of one of these pulses, just to show that it's quite wide in frequency. So it's actually driving all of these transitions at the same time, just manages to refocus them just the way we wanted them. So now if you can do snap gates and you can do displacements, using these blocks, you can not only create any state in the resonator, so there is a proof that they are universal, but you can also, with few of them, efficiently do it. So here I give an example of creating a single Fock state and like reading out the probability to have a single photon. But if we want some, let's say, a bit more complicated state, where we also have coherencies, such as, for example, this binomial state, which is supposed to be an equal superposition of 0 and 4 photons. We can get this by using sequence with 2 snaps and 3 displacements. And this is my best state yet. It's 91% fidelity compared to the ideal one. And with my current qubit T1 and T2, I'm expecting 95. So now I'm in the process of chasing these last few percent, either to add, you know, loss of my cavity in the simulation and some thermal excitation, so on, or to see maybe what are my coherent errors, meaning I didn't exactly perfectly calibrate my system. So apart from this one, so what would be the advantage of not doing kind of complete, you know, black box, just optimal control, is that now I can actually image my state after each one of these blocks, and hopefully this helps me pinpoint where my errors are. Actually, even better, it would be not to do the full Wigner tomography every time, but do this shortcut. As Jeff said, this is an over-complete representation. So I tried a few more states, you know, like a single Fock state, and this is some very small 3-headed cat. And yeah, it's working, which is a good thing. And to conclude, yeah, these are how they're supposed to look like ideally. So there is a bit of work left to be done. So to conclude, we managed to create these Wigner-negative states, and we used these optimized pulses to speed up the snap gates. And yeah, this error budget is still a bit of work in progress, and 95 is maybe some good target for now. And then to be done, you know, just keep it now I need to keep it alive, my state, not allow it to decohere, dephase, get ruined by Kerr, and so on. So yeah, thank you for your attention.
Thanks, Marina. Very good timing too. So it's open now for questions, and I didn't mention, but you can ask a question by posting it in the chat. You can raise your hand, and if I still have ignored you, you can still try to unmute yourself and just ask. So please. I see Jeffrey. Would you like to go ahead?
Marina, great talk. I noticed early on you have some finite one population in your cavity, some finite cavity temperature, but it actually looks quite low. I was wondering what you find most important about minimizing that.
Wait. So actually this picture is from like 1 week after the cool down. Now I have a picture with this amount of averaging. I cannot see this peak at all. So now I'm actually struggling to measure what's my cavity temperature. So my sample has been called for 6 weeks. So maybe just wait.
Patience.
Yeah, but yeah. So this was about 3%, I think, and now it's way lower.
Okay, cool. Thank you.
I see David Haviland. David, please.
Hi, Marina. Thank you for the nice talk. You mentioned how you use these optimized pulses to do the SNAP, and you explained how to get them through frequency combs, how to put these phase factors. But what you say then the SNAP is much shorter. But when you look at the SNAP, can you understand why it works afterwards? It's just an optimizer. Do you have any feeling for why it works?
Short answer, no. You can simulate and look how this SNAP, let's say, so if you look at this gate, so you can simulate and see like what it does after, I don't know, 10 nanoseconds, 20 nanoseconds, and so on. And I've been looking at them now for a few months for sure, and I can really not see, yeah, I cannot make any sense of it. Unfortunately,
you realize it has broader frequency, broader spectrum than just the comb drive, which make some sort of
yeah. So this one is definitely, even though I, let's say, want to just do a pi pulse on the pi phase on the 0, this one throughout he will drive all of the transitions, like all of the phases, but just let's say 50 nanoseconds before the end of this pulse, he will refocus everything.
Okay.
So and the interesting thing is that like qubit is kind of very close to the equator for most of the time of the pulse. So yeah, everything is precessing. It's just yeah, it gets refocused in the right way at the end.
Thank you.
Yeah.
So could you say that the other Fox states, they pick multiples of 2 pi? Would it be a good way to put it, or?
Yeah, sometimes, but sometimes they also kind of pick a positive phase and a negative phase and a.
Oh,
yeah.
I see. Yeah. Okay, I don't see any other hands, or maybe there is Anton for a last question.
Yes, just a quick question, Rina. So you said now that you had taking the qubit decoherence into account. Ideally, you could get 95% fidelity. How much would you need to improve the qubit to get 99%? Say, do you know that?
All right, we should run that simulation. Yeah, I don't know, but I wouldn't expect it to be unreachable, maybe 5 times. Yeah, let me get back to you on that.
Marina, would you like
Thanks.
to take a very last question from Jonas Bilander in the audience? What noise characteristics goes into the optimizer?
This one. For now, no noise. So there is a possibility to make these pulses robust if you have like a noise spectral density that you can measure, and you can also add like T2. It can echo out sort of things, but we didn't have time to try that yet. But it's something to try, definitely. Okay,
let's move on. Thank you very much, Marina.
Thank you.
And our next speaker is Antoine Essig from ENS Lyon. Hello, welcome.
Hello.
He will speak about multiplex photon number measurement.
Thank you. So good afternoon, everybody. My name is Antoine Essig. I come from the Quantum Circuit Group at École Normale Supérieure de Lyon in France. Before starting, I want to thank the organizer of this conference who invite me to talk about multiplex photon number measurement. And so before speaking about multiplexing, I want just to remind how usually we photo count. So we already had some good talk about it later. But so let's consider an harmonic oscillator. I will call this oscillator the storage mode. And it can be the first mode of a λ/2 resonator or the first mode of a 3D cavity. And so to count the number of photons inside, I will couple it to a qubit in the dispersive regime and more precisely in the number resolved regime. And so in this case, the qubit has a specific resonant frequency for each Fock state of the storage mode, exactly as we saw in the former talk. And so as Steve Girvin told us, we can, for example, drive the qubit with a pi pulse at this blue frequency corresponding to the Fock state 2. And if we find the qubit excited at the end of the measurement, it means that the storage state has indeed 2 photons. And so we can ask binary question about the photon number, encode the answer in the qubit state, and then read out it using a dedicated readout resonator. And we will ask as many binary questions as we need to know exactly the number of photons, and all those questions are asked one after other, so that the questions are asked in the time domain. And the optimal protocols is the binary decimation, so measuring the bits of the binary code of the photon number. And it was recently implemented using optimal control or feedback. And it gives a measurement time which scales as the logarithm of the maximum photon number in the storage mode. And so the question I will ask for the rest of my talk is it possible to improve the scaling? Is it possible to reach a measurement time independent of the maximum photon number n? And so nowadays, we have access to quantum limited broadband amplifiers. We can also multiplex our measurement. And so in fact, we can ask our questions in the frequency domain. What I mean by that is you can ask all your questions simultaneously and read out the answers at different frequencies. So let's see how we can indeed use this frequency domain to improve photo counting. So let's consider the storage mode here in a superposition of 3 Fock states. It is coupled to a qubit, and I will call this qubit the multiplexing qubit. It is coupled in the number resolved regime, so the number of photons is encoded in the frequency of the multiplexing qubit. And so what we want, in fact, is directly measure the frequency of the qubit. And for that, what we are going to do is to couple the qubit to a transmission line to probe the fluorescence field of the qubit. At the end of the transmission line, we have a multiplexer. So it is an array of filters centered on all the possible qubit frequency with a width chi-SMP, the cross-scale rate between the qubit and the storage mode. And after each filters, you have a perfect photodetectors. So how to reach a constant measurement time? let's start by prepare the qubit in an excited state, whatever is the state of the storage mode. So we use for that an unconditional pi pulse. And then we let the qubit spontaneously emit a photon in the transmission line. And so the frequency of this photon is entangled with the storage. And here, the 3 different colors represent the 3 different frequencies of the photon. The photon will propagate up to the multiplexer, which will transform the frequency entanglement into frequency and space entanglement. And at the end, it arrives on the array of photodetectors. Only one of those photodetectors will click, and this measurement will be followed by the projection of the storage mode, the storage state on the fog state, which correspond to this to the frequency of the photodetectors. And so in this case, the time to determine the number of photons is given by the time the qubit need to emit a photon in the transmission line. And if we have a strong, if we are in the strong coupling regime for the qubit and the transmission line, in this case, the time to do the measurement is only given by the T1 of the qubit, which will be only limited by 1/chi due to the number resolved regime condition. So right now, this experiment is a Gedanken one. Because the hardware resources, this multiplexer and the array of photodetectors are out of reach. But the ID, the 2 ID on which it is based, we can study them. So the first one is the ID we can photocount using the fluorescence of the qubit. And the second one is the ID we can multiplex this fluorescence measurement. And so for that, 1 year ago, we carry out an experiment where we replace this the unconditional pi pulse to probe the qubit by a frequency comp, which contains all the resonant frequencies of the qubit from 0 to 8 photons. And then we demultiplex the reflected frequency comp and perform a heterodyne measurement at every comp frequencies. So instead of a unconditional pi pulse, we have a continuous frequency comp. And instead of an array of perfect photodetectors, we have heterodyne measurement. And so I will show you now that with this setup, we can check that the 2 main ingredients of the Gedanken experiment works. So what are the constraints for the experiment? First, you need an IQ resonator. So in our case, it was a λ/2 resonator here in green. And you need a qubit coupled to a transmission line. So in the experiment, it was a transmission qubit here in orange, and you can see here the transmission line coupled to the qubit. And the 2 constraints you have to check is first, you need to be in the number resolved regime. And second, in order to have a fast measurement, you want to decrease the T1 of the multiplexing qubit, but due to the hybridization with the storage mode, it will also decrease the T1 of the storage. So you need to find some trade-off, and we succeed to do that by designing the circuit to have a T1 for the qubit of 15 nanoseconds, a T1 for the storage mode of 4 microseconds, and a cross-carry rate between the 2 of 5 megahertz. And so now we can, with this experiment and those parameters, we can check the first ingredient of the Gedanken experiment, photocounting using the fluorescence of the qubit. So for that, we start by injecting a coherent state in the storage mode, and then we perform a quantum limited spectroscopy in reflection of the multiplexing qubit. So at the end, we measure the reflected coefficient of the qubit at the frequency F probe. And if the length of the drive of the spectroscopy is long enough, driving the qubit at a frequency FMP minus N chi-SMP will lead only to a resonant fluorescence if there are N photons in the storage mode. And this is exactly what we measured. So here you can see the real part of the reflected coefficient as a function of the frequency F probe, and each dips correspond to a resonance of the multiplexing qubit for a specific number of photons, 0, 1, 2, and so on. And the depth of each dip is proportional to the probability to have the number of photons associated. So we are able to reproduce our data using a master equation model, and then you can repeat this experiment for various amplitude of coherent state, and at the end you finish with this 2D map where you have the real part of the reflected coefficient as a function of the amplitude of the coherent state and the frequency of the probe. And each spot corresponds to a specific resonance of the multiplexing qubit for a specific photon number. And you can see we are able easily to count up to 8 photons. So this 2D map is a proof that you can indeed photocount using the fluorescence of a qubit. Now we want to check the second ingredient of the Gedanken experiment. Are we able to multiplex this measurement? So for that, we want to probe simultaneously the qubit at the 9 frequencies corresponding to the 9 first Fock state. So how to perform this measurement? We use AWG to generate the frequency comb. Then we probe the multiplexing qubit with the frequency comb in reflection, and the reflected pulse is demultiplexed. And at the end, we have 9 record RK, where K is the number of photons probed by the record. So let's use it. We start by injecting a coherent state in the storage mode, and then we probe the multiplexing qubit with the frequency comb. And we demultiplex the reflected frequency comb. So this graph shows you 1 minus the real part of RK, so the depth of each resonant depth of the qubit, as a function of the mean photon number in the storage mode. And what is important is the 9 values for each value of NS, which correspond to the 9 values of K, are taken simultaneously with only 1 measurement repeated and average, because we are multiplexing the measurement. And in order to check that those data we understood those data, we are able to reproduce them using a master equation model. And so this is the proof you can indeed perform a multiplex photon number measurement using the fluorescence of a qubit. So now you have this new measurement, and what you want to do is to make it as fast as possible. And the first parameters you can tune is the amplitude of the frequency comb. But in order to find the optimal amplitude, you need to have access to the rate at which you extract the information outside of the system. In some other words, you want to measure the measurement-induced dephasing rate of the storage. And so for that, we forgot about the multiplex measurement, and we look at the dynamics of the mean storage state. How to have access to this dynamics? For that, we add a second qubit here in blue in the circuit and a dedicated readout resonator in purple. And it enables us to perform Wigner tomography of the storage mode. So this is the protocol we use. We start by initialize the storage state in a coherent state, and then we perform a multiplex measurement during a time t with an amplitude omega. And at the end, we measure the Wigner function of the storage mode. Using the Wigner function, we can reconstruct the AS plus AS dagger quadratus of the storage mode, and you can see that it shows an exponential decay with the measurement, the multiplex measurement time t. And from this exponential decay, we can extract the decoherence rate, which contains the measurement-induced dephasing rate of the storage mode. What is important is for each of those dots, you need a complete Wigner function. And in fact, you can already see the dephasing of the storage state on those Wigner functions. So now you can repeat this experiment for various value of omega. And at the end, you obtain the following graph, which is the decoherence rate of the storage mode as a function of the amplitude of the measurement omega divided by chi-SMP. And you can see that the measurement strength does not simply increase with the amplitude. And we are able to reproduce this behavior with a master equation model. And the optimal point, the point where you have the fastest measurement, is in fact omega equal to chi-SMP divided by 2. So why? So we developed a theory during the last year to explain this result. I will not have the time to explain you in details, but I will give you the main ingredient. So you are currently probing the system with a frequency comb. And as the Fourier transform of the comb is a comb, the time envelope of the drive on the multiplexing qubit is also a comb with a time step 1/chi SMP, and where each of those peaks correspond to an almost instantaneous rotation in the Bloch sphere by an angle 2 pi omega divided by chi. And what the theory we developed explain us is we need to maximize the excited population of the qubit to have the fastest measurement. And so for that, we want to make pi pulses. We want that those instantaneous rotation are pi pulses. And so omega max equal to chi, when omega is equal to chi SMP divided by 2, we check this condition. So to summarize from the point of view of performance, what I say, here you have a table which shows you 4 of the main time domain photocounting protocols and the 2 frequency domain protocols I show you today. And what you can see is the multiplex measurement using the heterodyne detection as a measurement time which scale as a state of the art. This is due to the intrinsic noise of the heterodyne measurement, and only the Gedanken experiment with the photodetectors can reach a measurement time independent of the photon number. From the point of view of the measurement, my conclusion will be the following. We show that we can indeed photocount using the fluorescence of the qubit. We can multiplex this fluorescence to perform a multiplex photon number measurement, and we are able to study the measurement-induced dephasing rate using Wigner tomography and to explain the dynamics of the cavity qubit system when it is driven by a frequency comb. The perspective for the futures is to perform a single-shot measurement of the photon number. But for that, we need to improve the T1 of the storage mode. And so we are working on a new 3D design. And you can see here pictures of the 3D cavity we are currently using. I want to thank you for your attention and also to thank my team, in particular Quentin Ficheux, who did all the experiments with me. He will talk later in the conferences. Alain Sarlet, who developed the theory, and the Lincoln Labs for the TUPA we use. Thank you.
Many thanks, Antoine. This is a really beautiful experiment. I really enjoyed this talk. I would have plenty of questions myself, but I would leave the floor to others to ask first. I see Yoshiki Tsunada, please.
Okay. Thank you for the great talk. Maybe a naive question, but can you replace the qubit with a resonator and just have a resonator coupled to a storage resonator with some cross-core interaction, and that way you can increase the probe power? Does that work?
So this is an excellent question, and indeed, if you do that, you can increase the power to when you probe your setup and have a fastest measurement. But the problem is to have this cross-scale rate between 2 resonators, which enables you to be in the number resolved regime. And so from my point of view, you have 2 choices. Either the 2 harmonic oscillator are have a medium level of nonlinearities, but this is most of the time not a great choice. Either one have a high nonlinearities and the other one a low one. And this is the case when you have a qubit and a harmonic oscillator. So I will just say, if you find a way to have this number resolved condition without too much nonlinearities in the storage mode, it will be an excellent improvement.
I see. Maybe use a quarton or something, but not my expertise. Thank you.
Any further questions? I was wondering, you speak of these Gedanken experiments, but let's say both your team and my former team have developed single photon detectors in the microwave. So why are you not looking into doing this for real?
So it just like, it depends, but if you want to do your measurement from 0 to 8 photon, you need 9 photodetectors which work pretty well. And you need to design on a chip this this array of filters, which are square filters. So it's just like, it's maybe not impossible, but it's a lot of work from the engineering point of view, and you will have 10 chips or a big chips with 10 different parts of the circuit on it, the 9 photodetectors and the main circuit. It's a great challenge, I would say.
Yeah, your photodetectors are naturally narrow band, so they filter a little bit themselves, probably.
Yeah, yeah, of course.
Okay, is it an efficient tomography method? Like, can you use it, let's say, suppose you want to do Wigner tomography, the standard way we know how to do it is that we displace and we measure the parity by mapping the parity into a qubit state. But is this a more efficient way to read out the state of a high Q cavity?
So this readout protocols is only sensible to the number of photons. So you will only have the diagonal of your density matrix. You will have no information about the coherence in between the Fock states. And in fact, you will even destroy the coherence when you perform the measurement.
True, but combined with displacement, you could measure some generalized Q functions.
We didn't have a look to that, so maybe right now I don't have the answer. But indeed, if you find a way to encode the information only in the photon number, you can do a complete tomography in this case.
All right. Thanks. Since I don't see any further question, I'll take my last one.
Okay.
And, you're looking at measurement-induced dephasing as a measure of how efficiently you are extracting the information.
Yeah.
On the other hand, when you look at the reflection coefficient, you're only looking at the coherent part of the scattering. There will be incoherent scattering as well. So you could have a large measurement-induced dephasing, but little information that you're looking at. So.
Yeah, this is an excellent question. And in fact, it's even like, from the dephasing point of view, what is important is the sigma z component of the qubit. So how much it is excited during your measurement process. This is why you want to, we have this specific value omega equal KSMP as an optimal point. But from the point of view of the measurement, what you want to do is to improve, to have the highest sigma y, sigma minus value from the point of view of the fluorescence. And so this is, yes, indeed, why photodetectors are better than heterodyne measurement, because they directly measure the sigma z component, whereas the heterodyne measurement measures the sigma minus. You can reconstruct sigma z, but you have the quantum efficiency square. So it is maybe worst, in fact. So what you have to do is to do a trade-off. You will have to decrease the speed of your measurement to increase the speed of the so to decrease the decoherence rate to increase the measurement rate, and at the end, the only thing you want to do is to have the fastest measurement rate, of course.
Okay, I think if we want to talk more, we'll have to take it offline. So thank you so much.
You're welcome.
Let's move on with the next speaker of today. Martina, are you ready?
Yes. Can you hear me?
Martina is from CNRS Grenoble. She will speak about the reverse Kerr traveling wave parametric amplifier. Looking forward to your talk, please.
Thanks, Simone. Yes, my name is Martina Esposito. I'm a postdoc here in Grenoble at the NIST Institute. Before starting, I would like to thank the organizer for giving me the opportunity to speak at this workshop, and also want to mention that I really appreciate the Swedish pastry that you sent us. This was indeed a very nice idea. Thanks a lot. So in this talk, I'm gonna give you an overview of our last results about developing a traveling wave parametric amplifier with a new phase matching mechanism that we call reverse Kerr phase matching. So just to start, a quantum noise limited amplifier is a very important tool in many frameworks, in particular in quantum technologies. And every amplifier has a figure of merit, which is very important, which is the added noise. So this added noise can be expressed in terms of noise temperature, and the minimum noise temperature an amplifier is basically the standard quantum limit noise temperature. So the goal is to develop an amplifier that can reach a noise temperature very close to the standard quantum limit. And in fact, typically in experiments, what you don't have just one amplifier, but you have a chain of amplification, and you can show, and typically this amplifiers are sitting at different temperature stages, and you can show that the noise temperature of your chain is mostly dominated by the noise temperature of your first amplifier, provided that this noise, that this amplifier has a gain which is high enough. So this is a very important point, because this is the motivation that brings us to develop noise quantum limited amplifier with the following targets. So for noise target, we want to reach the standard quantum limit, and as gain target, we want to reach typically 20 dB, which is the typical gain you need to be in this approximation. Our amplifiers are parametric amplifiers. So in parametric amplification, you have a wave mixing process, and typically this is true in general for all parametric amplification processes. You have a nonlinear medium, and your signal is getting amplified thanks to the energy provided by a pump field and via the generation of an idler field. And for example, in the case of four-way mixing amplification, you need to verify the energy conservation relations and the momentum conservation relations in order to have optimal amplification. So in Josephson parametric amplification, our nonlinearity is coming from some Josephson element, so an element which contains a Josephson junction. And the nonlinearity can be expressed looking at the current phase relation, where the current through the junction can be expressed as a nonlinear function of the phase across the junction. And in particular, you have two main nonlinear terms, beta and gamma, which corresponds in the language of nonlinear optics to the chi2 and chi3 susceptibility. And these are the nonlinearity that we want to use in order to achieve amplification using these Josephson junctions. So in our case, we work with traveling wave parametric amplification based on Josephson junction. And the idea is that you have this nonlinear medium, which is composed by a long array of Josephson junctions. By long array, I mean something of the order of 1,000 junctions in an array. And these traveling wave parametric amplifiers are very useful tools, because you can reach very large bandwidth of the order of few gigahertz. However, it's not so easy to develop them, because one of the main issues is this one, is the phase mismatch issue. This is a critical issue in the developing of traveling wave parametric amplifier. And in this talk, I'm going to show you a new way that we developed here in Grenoble to solve this issue of the phase mismatch in two paths. So generally, when you have a Josephson-based traveling wave parametric amplifier, you have many unit cells, and your unit cell can be composed, for example, by a single junction or by a squid. And then the size of your cell is much smaller than the wavelength of interest. So you can describe the dynamics of this nonlinear transmission line with this wave equation. And you see that the nonlinear coefficient gamma is the key point here, because this nonlinear coefficient is responsible for the four-way mixing or Kerr nonlinearity, which is responsible for the amplification. However, it's also a problem for the phase matching. In fact, if we now sort of divide this wave equation in two parts, in some, let's say, linear part and non-linear part, we can see that the total phase mismatch is given by two different contributions. The first contribution is this delta K0, which is coming from this part of the wave equation, and is basically coming from the fact that the dispersion relations in this transmission line are not perfectly linear. This means that since the dispersion relations are not linear, then we will have some phase mismatch that we call delta K naught. In addition to this phase mismatch, we also have the Kerr phase mismatch that is coming directly for the Kerr nonlinearity. And in total, we get this delta K in green here, which is the total phase mismatch. And this is the problem that we want to solve, because our gain is maximum only when this delta K is equal to 0. So how do we solve this problem? So typically a possible solution is to use some dispersion engineering approach. So in dispersion engineering, what you do, you go and somehow modify this term here by modifying your dispersion relations. So I'll give here 2 examples of devices in which dispersion engineering is adopted to obtain phase matching. So in the first case, the dispersion engineering consists in opening a stop-band gap in the dispersion relation by adding a resonant element in the unit cell, basically. And this is the gain that is obtained in this device. In this other example, the dispersion engineering is based on the opening of a photonic gap in the dispersion relation by modulating the size of the Josephson junction, so the dimension of the Josephson junctions in the transmission line. So this is in fact great. Dispersion engineering works very well for achieving phase matching and for achieving high gain of the order of 20 dB in a large band. However, there are some things that we can still improve in this, starting from this approach. For example, the limits of this dispersion engineering phase matching are that you achieve phase matching only for a fixed frequency, which is the frequency at which you open the gap in dispersion relations. In addition, the fact that you're opening this gap in dispersion relation is also responsible for the presence of some gain ripples in the gain profile. And also you have this band, this gap in the middle of your gain profile, which can be undesired. So the question is, can we do better? So can we think at a new way, at a new mechanism to achieve phase matching in these devices? And this is what we try to do. So we worked on this reverse Kerr phase matching. And basically the idea is the following: instead of focusing on this part of the phase matching, this delta K0, we focus on the delta K Kerr, so on the phase matching coming from the Kerr nonlinearity. And in particular, we want to reverse the sign of this delta K Kerr in order to balance this term and have a total phase mismatch equal to 0. And in this way, we don't need any dispersion engineering. So the approach we adopted is the following. So this is the schematic of the device that we developed. Instead of having just a single Josephson junction in our unit cell, we now have a snail. So the snail element is a superconducting nonlinear asymmetric inductive element. It's composed by a loop with a small junction in one arm and 3 big junctions in the other arm. So this element is very nice because we can now write down the nonlinear current phase relation, and we see that we have 2 components, a 3-way mixing term and a 4-way mixing term. And now we can write the wave equation for the propagation of the waves in this nonlinear transmission line in the following way. The key point here is that both the 3-way mixing nonlinearity and the 4-way mixing nonlinearity are now tunable in situ, because now we can tune beta and gamma by tuning the external magnetic flux that is threading the snail loop. And this is very important. In fact, here I'm showing you the beta and gamma versus the external magnetic flux, which is something that we can easily change in situ in our device. And in particular, we want to work at this sweet spot here, where the gamma coefficient is maximally negative. So in fact, we reversed the sign of the Kerr nonlinearity, and also the beta coefficient is 0. So we should have no 3-way mixing processes. So at this sweet spot, what happens is that now our delta K Kerr becomes negative because it's proportional to the Kerr nonlinearity. And this means that we can achieve phase matching using this new reversed Kerr phase matching mechanism. So I'm going to show you now the results. So this is the gain profile of our device obtained using the same device, just pumping the same device at different pump frequency. In this case, in the blue curve, we are pumping at 6 gigahertz, in the red curve at 8 gigahertz, and in the green curve at 10 gigahertz. And we can reach high gain of the order of, we hit the 20 dB, let's say, target with a large band without the gap in the middle of our gain profile, because we are not using any dispersion engineering approach. And the dashed lines here are theory without any fitting also, we show that this approach helps a lot with using the gain ripples. So here I'm plotting in red the reverse Kerr tupa, and in gray the dispersion engineering tupa from our group here in Grenoble. And you can see that if now you look at the standard deviation of the gain, we have reduced a lot the ripples using this reverse Kerr phase matching. In this slide, I'm going to show you the performances in terms of noise. So in blue here, you see the experimental results for the noise temperature of the tupa, the added noise temperature of the tupa, compared with the theory obtained by numerically solving the couple differential equations, and in green the system noise, which is the noise temperature of the entire amplification line. And you should compare these curves to the pink one here, which is the standard quantum limit. So we could achieve a noise temperature of the tupa, which is roughly twice the standard quantum limit at the peaks of the gain. And this is comparable with other tupa based on Josephson junctions. Okay, so I'm going to conclude. I hope I convinced you that we can now use this new phase matching mechanism for traveling wave parametric amplifiers based on the idea of using a Snell unit cell. And we could achieve 20 dB of gain in a large bandwidth with the noise temperature comparable and 1 dB compression point comparable with the devices of the same family. And with this, I would like to thank the amazing colleagues that I have the pleasure to work with here in Grenoble at the NIST Institute, in particular Nicolas Roth, who is leading the tupa team, and Luca Plana, who started this research line here in Grenoble with his PhD and now is a postdoc here. And in particular, Arpit Ranadiv, who is the PhD student directly involved on the project of the reverse Kerr. And thank you very much for your attention.
Thanks, Martina, for a very interesting talk.
Thank you.
And now the floor is open for questions. I see Kiming Chen.
I have a very naive question. So I see you call one photon as a standard quantum limit. So my question is that why it's not half a photon? So
yes, because we consider the contribution for signal and Idler.
okay, I see. Thank you.
I'm not sure in which order, but there was Maxime.
Sorry. Yeah, I have.
Oh, sorry. Yep.
I have a very basic question. How much pump power do you need to pump this this amplifier, and also how homogeneous your flux needs to be?
Yes, for the flux, we verify that we are just using a magnetic coil. The flux, I mean, we are not limited by the magnetic flux. It's more the homogeneity, if you want, in magnetic flux is more given by the imperfection in the fabrication of the superconducting loops. And we did some simulations, and we think we can have a few percent of inhomogeneities due to the different, let's say, imperfection in the size of the loops. For the pump power, I think it's comparable with other Josephson junction-based device. I don't have now by heart the numbers, but yeah, I would say comparable with the same family of same devices.
Thank you.
Okay, Martina, you got really very many raised hands.
Okay.
So let's try and be quick. I think there is Hampus next.
Yes, hi, thanks for the presentation.
Hi.
I'm wondering if you have any, because the gain profiles we're looking at now, they are at that sweet spot of the DC flux, right?
They are, yes.
Do you have any figure with a comparison to when you don't have a DC flux?
Yes, so I don't think I have the plot right now, but with, let's say, at zero flux, we achieve 15 dB maximum of gain, because in that case, you are not phase matched, basically. And yeah, in that case, you have the standard four-way mixing gain profile, symmetric around the center, around the pump. But the maximum gain there is 15 dB.
Right. And then, can I ask another question? No, maybe not.
Sorry, Hampus, I think I'll ask David to ask his.
Just a comment that thanks for the very interesting talk, but in this new method you're presenting of compensating dispersion really with nonlinearity, that sounds a lot like the Korteweg-de Vries equation where you get soliton solutions. Have you thought about that? There might be a soliton propagation in this line.
Yeah, it's the same physics, yeah, of soliton propagation when you have both dispersion and Kerr nonlinearity contributing to your propagation. I think that the formalism is very similar to how you describe soliton, and indeed this is a direction that we have in the back of our mind to look at soliton generation in this kind of devices.
Thank you.
All right, now Alejandro.
Can you hear me properly there?
Sure. Yes.
Yeah, so I assume that what you're doing here is you're applying a flux that is equal on all the snails, right?
We do, yes.
All right. So and then you show this graph where you have these two contributing terms, the red one and the blue one.
Yes.
The two nonlinearities, and I guess the red one we are like on a spot where the sensitivity is high, right, for the external magnetic flux. So I was wondering how this high sensitivity, I don't know, like if you have any comments on that.
Yeah, that's a very good point indeed. I mean, this device has a very rich physics. So in this talk, I just focused on the four-way mixing amplification, but in fact, since we can tune the nonlinearities, we can look at three-way mixing processes. And in fact, since the beta is very, the derivative is very high at the sweet spot, if you really, basically, you would like to kill all the three-way mixing processes, but this is not so easy. In fact, we are now trying to look, for example, a second harmonic generation, which is the main three-way mixing process that you can observe. And we are looking now at if we can actually kill off the third harmonic generation completely. And this is, as you said, is not, is somehow limited by the fact that the derivative of the beta is very high. But you can tune this by the design that you choose for the snail.
All right, thanks.
Okay, I see two more raised hands, but we have to move on. So I invite those people to ask privately to Martina. I'm sure she will be happy to take those questions. Thank you very much.
Yeah. Thank you,
again.
Simona.
Thanks. And we move on for the last speaker before we have a short break, who is Maxime Malnou from NIST. And he will speak of the noise performance of a three-wave mixing kinetic inductance traveling wave amplifier. Please.
Okay, thank you. Can you see my slides?
Yes, very well.
Okay, thank you. So hi everyone. Thanks for inviting me at this workshop. I'm Maxime Malnou from NIST, and today I'm going to talk about our efforts to replace amplifiers at 4 Kelvin with kinetic inductance traveling wave amplifiers, or KITs in short, like the one I show in these pictures. And so for the millikelvin operation of this type of device, you can go check out our recently published paper. As you all know, a HEM typically dissipates a few milliwatts of power at 4 Kelvin, and as we scale up quantum computers, eventually we're going to face the same challenges than satellites missions, where the hence power consumption drives the design of the whole project. And for example, in mission like the LYNX X-ray Space Telescope that I'm presenting here, there's going to be an array of sensors that will be read out by 16 HEMTs placed at 4.5 Kelvin. And those HEMTs, they account for 70% of the power load at that stage. So reducing the power requirements for the 4K stage amplifiers is no small issue for that type of missions, and also eventually for quantum computing. Now, we also know that the HEMT at the noise is a few Kelvin. And so in comparison, when we look at a traveling wave amplifier like a kit dissipates only about a microwatt of power. So say 1,000 times less than a HEMT. And furthermore, because we fabricate it with NBTIN, whose critical temperature is 14 Kelvin, it still works at 4 Kelvin. Now, traveling wave amplifiers are known to be broadband, and kits in particular have high saturation power, so they are compatible with high channel count applications. And finally, while we demonstrated that it's near quantum limited at millikelvin temperature, we actually think it could be just as good at 4 Kelvin. And this is what I'm going to talk about. Because you see, conventionally, a PARM can be thought of as a 2-port device where you have an input and an output, a signal input and a signal output. And N, the added noise N, is seen somewhat of an internal degree of freedom. And so when there's no excess noise, when there's no interconnection loss, this amplifier is called quantum limited. But really, this noise N actually comes from the input idler mode. And that's why it's better to think of a PARM as a 3-port device, like Martina shown actually. And therefore, then here you have a signal input port, an idler input port, and a signal output port. And then the quantum limited nature of this amplifier just comes from the fact that the idler input port is cold. And so now, what might sound surprising to you is that if you place the power amp at 4 Kelvin, but if you keep the idler input port cold, you can still get quantum limited performance. Of course, this is provided that the loss, and in particular the loss at 4 Kelvin before the power amp, is minimal. Otherwise, this loss term is going to completely dominate the overall added noise of the amplifier. So to test this idea, we're going to use a kit as our traveling wave amplifier. And this slide is basically a summary of how our kit works. So it relies on the kinetic inductance that I'm writing here. And actually, when you add a DC bias on top of your pump current, you're going to be able to pump your kit in a 3-wave mixing fashion, because basically thanks to this term here. And so 3-wave mixing has several advantages over 4-wave mixing. 1, the pump power is much lower, and 2, the pump tone is actually far detuned from the amplification band, so it's better for filtering. Now, the phase matching condition in those kits is expressed, I wrote it here, where the K's are the wave numbers for the pump, the signal, and the idler. And so what we do is we do dispersion engineering to have a line that respects this condition. And more precisely, the line actually looks like this. So it's a NBTIN CPW type of line, where in blue here is the ground plane and in red is the central part of the line. And what we added some IDC fingers on both sides. And we also change periodically the impedance of that line. And so it essentially gives us 2 things. First, the line is matched to 50 ohm, and also we control that way the phase matching bandwidth, so the bandwidth over which we have this phase matching condition that produce exponential gain. So the actual device looks like this. It's a 2x2 centimeters chip on which we have patterned a line that is 33 centimeters long, and you see that it's arranged in a spiral with there's the input here and the output there. And if I zoom in, you can see the periodic loading here, where some fingers are shorter periodically in the line. And if I zoom further, you can see the line here where you have 1 micron wide fingers. Now, because we have a CPW, it's actually a bit tricky to correctly ground the chip, especially in the middle. And so that's why we did this trick where we put some springy pogo pins that you can see here that descend from the top of the packaging, and they contact the chip in between those line traces. The other advantage of using this pin is that it also helps thermalizing the chip. So okay, so we put this kit at 4 Kelvin, and we measured the system at the noise of an amplification chain that looks like this. with a shot noise tunnel junction. And so this junction, I'm showing you a picture of this junction here. And it's basically a device that when DC bias is going to generate a shot noise whose value directly depends on the voltage bias across this junction. So that's what I'm showing on this graph here, where you have on the x-axis the voltage bias expressed in units of photons, and on the y-axis the noise in photons delivered to the chain. Now between the junction and the kit, you have some loss at 30 millikelvin, you have some loss at 4 Kelvin, and you also have some loss between the kit and the HEMT. And yes, we actually kept the HEMT here because for the time being, the kit that we fabricated can only reach about 16 dB of gain. And so finally, at the output, we are going to measure the noise on the spectrum analyzer. So now what I'm going to try to convince you on this slide is that the idler input port is super important because the noise from the shot noise junction also enters this port because the shot noise junction is wideband. And if you don't include this noise in your analysis, this is what happens. In essence, you have an amplification chain with gain G sub C and effective added noise NF. And this effective added noise represents any technical noise that you have. So if you do a perfect job, NF is equal to 0. Now at the idler input, you have a noise N, which when the amplifier is called is just half a photon. And so your output power looks like this. And then you find the system added noise N sub sigma here by varying N sub N, and then you do a linear fit and you interpret the y-intercept as being N sub sigma. But now if you include the noise generated by the shot noise junction that enters the idler input port, your output power looks like this. And in the limit where the input signal and idler noise are equal, you can rewrite it like this. And so now your interpretation of the y-intercept is completely different. And so let's say if you were getting a half quantum in the first case, and you were super happy because it meant that your amplification chain was quantum limited, when you recast this result in the second, which is a true case, it actually means that N sub F is twice that, so 1 photon, and your chain is not quantum limited at all. So you have to be careful and include this idler input noise when you do those noise measurements. So yeah, I don't have time to talk into too much detail about the full experimental setup, but I wanted to present it to you here, mainly so you understand where the loss comes from. And you see that there's quite a few components between the shot noise junction and the kit, and then between the kit and the HEMT. And all those components, they insert loss. So as I said, we operate the kit with about 16 dB of gain, which is what I'm showing on the top panel here. And this gain is symmetric about the half pump frequency, about 4.4 gigahertz or so here. And this is because once again, we pumped the kit in a through-wave mixing way. Then at each frequency, we're going to record the output noise while varying the voltage bias on the junction. And this is what I'm showing you here on this panel. So the voltage bias is here. And here on the y-axis is the output noise temperature divided by the gain of the chain. And so I'm showing you 3 curves for 3 different frequencies. And then the black lines are the fit of these curves from which we retrieve the system noise temperature T sub sigma. And this system noise temperature I'm showing you here on the central panel. And so I show it for 2 different situations when the kit is on black and the kit is off in purple. And so you see that when I turn on the kit, I reduce the system noise temperature from say around 15 Kelvin down to around 7 Kelvin. Now, one important thing also is that the T sub sigma is not just the added noise temperature of the kit or the added noise temperature of the HEMT. It's the noise temperature of the whole chain. That is to say, it's the noise temperature that the device replacing the shot noise junction here in our case would see. So these temperatures may seem high to you, especially if you compare to a HEMT datasheet where you're going to find a system noise temperature for the HEMT that is typically around 2 Kelvin. But this is where there's a difference between the intrinsic added noise of an amplifier and the system added noise you get when you put this amplifier in a readout chain. And this added noise is degraded by loss. And so we made a loss budget by measuring the transmission of those individual components at 4 Kelvin. So the various isolators and directional couplers and bias Ts and so on that you've seen in the full schematic. And we estimated their contribution to the noise on the various stages of the chain. And this is what I'm showing you here. And so you see that even though we have close to 4 dB of loss at 30 millikelvin, and this is because we have a long chain of components in front of the short noise junction. It only contributes to, this loss only contributes to about 4% of the overall output noise temperature. And this is because what enters here is cold loss. Now, conversely, we have less than 1 dB of loss at 4 Kelvin before the parent, but this is actually the major contribution to the output noise temperature, because this time what enters the chain is 4 Kelvin noise. So now, if you compare the influence of the cold and the warm insertion loss on T sub sigma, you have a plot that's going to look like this, where you see on the x-axis I represented the warm insertion loss, and on the y-axis the cold insertion loss. And so the star point represents where we are currently. And so you see that reducing the warm loss by just, say, around 0.2 dB is going to bring you from here to, say, around here. So you win 2 Kelvin of system noise temperature. And you see that you have to do a much harder job on the cold insertion loss to reach that, to have that type of improvement. So it means that this is super critical. This loss here is super critical. And that's why, and this loss comes mainly from the kits packaging, actually. And so that's why we're developing solutions like superconducting PCB. Now, to be confident in our noise measurement, we actually performed another noise measurement independent of the first one, because actually we mounted the short noise junction on a variable temperature stage. And so that way, if we keep the short noise junction at 0 voltage bias, where it looks like a 50 ohm load, we can actually input a non-thermal noise in the amplification chain, and also get T sub sigma that way. So this is what I'm showing you here on this central panel. Now, if I overlay the results with the previous results, you see that there's actually quantitative agreement. So it gives us confidence in using the short noise junction. And using a noise source like this has actually several advantages. It has a higher dynamic range. It's also a faster measurement. So finally, you see in this chain, we have additional microwave components that you've seen in the big experimental setup that we need to have to operate the kit. And we would not have them if we were only using the HEMT. So to make a fair comparison, we actually measured the system noise temperature of the chain when we removed the kit, and we also removed all those mandatory microwave components. And when we do that, we get a system noise temperature that is in purple here, that is around 5 Kelvin. And so it's not too far from the system noise temperature that I was getting with the kit on. And so once again, it's also important to understand that it's pretty straightforward to improve the chain's noise performance when the kit is there, because we just have to reduce the insertion loss, and especially the warm insertion loss. So now we could also compare this chain with the HEMT that we have with the HEMT alone with other chains. For example, we could completely remove the HEMT from 4 Kelvin. And because we only reach so far 16 dB of gain with our kit, we could think of putting 2 of them in series. But we could also keep the HEMT and put it at 40 Kelvin and see if this chain yields a lower system noise temperature than this one. And if we manage to prove that, it's still a huge win for satellite mission and for the scaling of quantum computers, because HEMT, because the 40 Kelvin stage has much more cooling power than the 4 Kelvin stage. So in conclusion, I showed you today a new way you can play with parametric amplifiers and using them at 4 Kelvin. And you can see how they are competitive with HEMTs, for example. And it's interesting because a kit in particular only dissipates about a microwatt of power, so much less than a HEMT. It's also interesting because any paramp even at 4 Kelvin can be in principle quantum limited. Now in practice, if I just put the kit I have in front of the HEMT and I look at how it improves the system at the noise, well, when I turn it on, it's going to improve the noise by about 50%. And if I do a more fair comparison between the noise of the chain that only contain the HEMT as the amplifier, I get roughly comparable performance with the kit. And finally, I also showed you that you can be confident in using a short noise junction as your calibrated noise source, because it gives you the same result than a variable temperature stage. So yeah, we're working on this. We're trying to reduce the packaging loss, and also we are also trying to completely remove the HEMT for the 4K stage and do a full demonstration of that idea. All right, and I think that's it. So with that, I thank you for your attention.
Thank you very much for an interesting talk. I think with the last 2 talks, we've covered 2 of the most promising TUPAs in the market. So thank you so much. and let's open for questions. Hampus, are you from the previous, or you want to ask something now?
No, I want to ask something here as well.
Please.
All right, so actually I have two questions, but in case I only get to ask one, I'll take the one I think is most important. So could you go back a few slides to where you had that gain profile?
Yep. This one?
Yeah, there, yes. Where did you say you had half pump frequency on this?
Oh, it's around here.
Right, right.
Yeah.
Good. Well, that's what I thought. Why is not gain the most there? Why is it not the largest there?
Oh, so this is because, so you see, so to answer your question, I'm going to go back to this phase matching condition. What we do is that the answer of your question is that it's because in this particular, at this particular central frequency, the phase matching condition is not perfectly fulfilled. And this just depends on the pump frequency that we used. And so actually, when you change the pump frequency, your gain profile is going to change from being something like this, where the maximum gain is here and then it goes down and then it goes back up, to something that is more flatter or something that is more round in the middle. And this just means that the phase matching condition here is just perfectly fulfilled for a frequency for a signal frequency that is around here, an idler frequency that you don't see in this graph that is around here, and then it's less fulfilled here. So yeah, that's the answer. It's just changing the pump frequency that changes the profile of the gain.
And now we can actually kind of touch to my other question, so maybe I can ask it because it's relevant. But that phase mismatch condition you had, like, why are there twos in front of these, idler K vectors?
So I think this two is because, once again, this is the three-wave mixing phase matching condition, and so you find it by having actually solving the telegraph equation in which you input this as your nonlinear inductance, and then you do a harmonic balance trick in which you keep only the frequencies at the pump signal and idler, and you're going to find this. But what I'm trying to say is that this includes the three-wave mixing term that is here and the four-wave mixing term that is here. And so those two basically come from the fact that it's three-wave mixing that we're interested in here.
Right. It's just that I do research on three-way mixing on 2+ as well, and I've never seen those twos. But maybe that's because this is a kinetic reference.
Yeah, I mean, it's just yeah, it's solving the couple mode equations in the case where you're interested in three-wave mixing.
Yeah, I know, and that's what I've done as well, and I don't have those twos, so that's why I'm confused right now.
Okay, I mean,
that's due to the kinetic inductance equations, maybe they're...
Yeah, exactly. Yeah, it's also that, for sure.
All right, yeah.
All right. I would like to ask Kiming Chen to ask the next question.
Hello, thanks for the nice talk. One point I didn't understand. So in the diagram, you have a signal, you have idler at 30 millik or something. But when your KIT is summarized at 4K, the idler should be dominated by the black body radiation at 4K, right? So this amplifier is not quantum limited anymore.
I'm not sure. And can you rephrase? I'm not sure I understood your question.
So because in your diagram, your idler is the 30 millik black body radiation. But if your KIT is summarized at 4K, and the black body radiation at 4K should dominate your idler.
Yeah, the thing is that it doesn't matter for paramps because the noise in paramps only comes from the idler input mode. This thing can be hot, it doesn't matter. I mean, it doesn't matter in the sense, so ideally it doesn't matter. Now, it might increase the excess noise that you would have, but ideally, it doesn't matter. Now, I agree that your excess noise, your technical excess noise might increase, but this is for other reasons that we are actually looking at. For example, maybe the amount of quasi-particles that we have and so on. But this has nothing to do with really the thermal. This noise here, the quantum limiting nature, has nothing to do with the thermalization of the device.
So the picture in my mind is that as long as your connector is normalized to 4K, it should matter, right? Because your signal should go through the connector.
No, I mean your signal comes from 30 millikelvin, and your idler also comes from 30 millikelvin. And so, yes, your idler is going to be degraded by those losses, well, like I said, and this will hurt you, that's for sure. But that you can work on. There's nothing fundamental that tells you that this is only 4K. This is only the noise temperature is 4 Kelvin. And actually, we actually see, if you look at this, the HEMT actually here that we measured has a spec sheet of around 1.5 Kelvin. All right, so it's already less than 4 Kelvin. And so you see that the kit plus all the other components are competitive with that. So it means that the kit itself is has a noise temperature less than 4 Kelvin.
Okay, I see. Thank you.
Yeah, I think I have a little bit of a related question. Maybe I could take it as the last. Yeah, I think I totally understand your point and your error budget. Okay, if all these connectors were lossless, you could have the connectors as physical temperature and the modes are a different one. Yeah, but or maybe that's a way to put what you're saying, that the propagating modes, they come from the cold stage, so they're still cold. And if you don't have attenuation, you don't have thermalization either.
Exactly.
It's
That's
a
right.
point I also like to sometimes make this way. But
That's
still,
exactly right.
but still, your thing performs worse than the HEMT, and now you're blaming it all on packaging. And I am a little wondering whether I mean there could be also losses inside the device, like big dielectric losses. And
there are some. And actually, you know, when I make this budget, I see that you have an excess of photon here that is around 4 photons or so. This is something we're working on, so this is preliminary results. So I'm not claiming that the kit right now is quantum limited. I'm just claiming that with the kit that we had, we put it at 4 Kelvin, the noise performance are promising.
Yeah. So
once again we didn't really we used the kit that we had, and we didn't really do we didn't spend time in really improving the packaging to make it as low loss as possible.
But let's say between packaging, dielectric losses, and quasi-particles, you don't really have a feeling how much they play or how much they contribute to these 4 photons.
Well, yeah, no, that is so. Yeah, that is correct. That is a correct statement. It's something that we are working on, discriminating what comes from the packaging itself and the kit itself. That's true. Yeah.
Okay. It's a very interesting and promising attempt, I'd say. So thank you very much for presenting it today.
Yeah.
And this was the last talk of this part of the session. We will take a small break now and convene again at 7:40 Central European time. And I would like to ask the speakers for the next session to be there 5 minutes ahead of time so that they can test their slideshows. So see you very soon. Okay, welcome back. Anne-Marije, you're next. Would you like to try your slideshow?
Yeah, sure. 1 second. Let's see. Sure. Can you see it?
Yes, perfect. Thank you.
So do you want me to start or wait a second?
Let's wait. We have 2 minutes to go.
Okay.
And in the meanwhile, perhaps I will also ask Lucan and Quentin to share their slides. Can you unshare the screen just for a second?
Again, yeah.
Yeah. Lucas, are you there? I can't see him yet.
Okay, I can try sharing mine. Hi.
Yeah, please.
Is it working?
Yes, it is.
Okay, thank you.
Okay, Anne-Marije, please share your screen, and we still wait a minute, but then we start sharp on time.
Yes. 1 second. Like this, right?
Yes, perfect. And this is 7:40 now, so we're good to start. Our next speaker is Anne-Marije Zwerver from QuTech and Intel, I suppose.
From QuTech, yeah, it's a collaboration.
And she will speak about qubits made by advanced semiconductor manufacturing. So please.
Thank you. Well, good day, good morning, good evening, good afternoon, everyone. So first of all, I would like to thank the organization for inviting me to this interesting and very nicely organized workshop. My name, yeah, as you said, is Anne-Marije Zwerver, and I'm a PhD candidate in the group of Lieven van der Sijpen in Delft. And after seeing all the nice talks today, I think this talk will be maybe a bit of an exotic excursion, as in our group, we are working with spin qubits in semiconductor quantum dots. But still, I think it might, yeah, I'm very excited about the results. So I'm really happy to share our latest results on the collaboration that we have with Intel with you. Let's see if I can, yeah, go to the next slide. Exactly. So let's start with spin qubits. We store our quantum information in the spin state of an electron. So we catch such electrons in semiconductors, a device such as shown here. And we do that by stacking materials such that we create a two-dimensional electron gas, so a 2DAC. And by means of metallic top gates that you see here in yellow, and actually also here, we can repel and attract electrons, and therefore we can create a potential landscape such that we can, yeah, basically curve out a potential landscape and catch electrons in quantum wells or potential wells. And we call those quantum dots. So you see that here, right? You see two quantum dots that are, yeah, in a potentially shaped landscape. And by applying a magnetic field, we can split the spin states into a two-level system, and we use them as a qubit. And neighboring electrons can interact by means of tunnel coupling. So spin qubits have lately presented themselves as promising qubit candidates. First of all, I show you some metrics. So we have a relatively long coherence time. You see here T2 of about 28 milliseconds. Moreover, we have a single qubit gate fidelity now of over 99.9%. And only recently, my colleague here in Delft managed for the first time to get a 2-qubit gate fidelity of over 99%. So we're really excited about that. So secondly, as you might see already here, spin qubits or these structures look a lot like transistors as we know them. And well, you only have to look at your phone to see that transistors are really, really small, right? There are millions of transistors on a chip. So also our qubits are relatively small in the order of 50 to 100 nanometers. And a third thing that's often said about spin qubits in semiconductors is that they're compatible with the semiconductor industry. Nevertheless, this has never been shown before, and this is what I want to find out in this talk. So we believe that fabricating our quantum chips in industrial clean rooms is beneficial for 3 reasons. So first of all, we want our yield to be high. Of course, if we want to scale qubits, we want all of our qubits to work. And with their years of expertise, we think that the semiconductor industry can increase the yield for our qubit chips. So then secondly, in the semiconductor fabrication lines, we in the end expect higher uniformity of samples, which would eventually decrease the number of input and output lines that have to go into our fridge. And finally, we expect that the charge noise will be reduced, and that means higher fidelity qubits. So there are also other companies that also fabricate quantum dot samples in 300mm wafer fab, so in industrial fab, and make qubits of them. For example, CA-Leti in France, and also IMEC in Belgium. So you see, yeah, they made quantum dot structures, and you see the qubits that they made. Nevertheless, their qubits are not single shots, so this is not scalable. And moreover, for their crucial fine gate structures that we make our qubits with, so the small gates, they still use e-beam lithography, and in some cases liftoff. And well, these techniques offer a lot of flexibility, but it's also very slow. And moreover, there are indications that these techniques might cause damage to the material, and this results in increased charge noise, so low fidelity qubits, and therefore, yeah, these techniques might be hard to scale. The samples that we use in this work are fabricated in a 300mm Intel facility, basically the same one as where the new generations of computer chips are made. And they are fabricated entirely using optical lithography, etching, and chemical mechanical polishing techniques that, yeah, that are used for years already to make transistors, and they work really well, but they're also very rigid. And well, it's just to see whether it's true, whether the more fragile quantum dot structures can be made with these techniques, and also whether they allow for qubits. So here you see a wafer. I thought the wafer 300mm, and I used to put a banana for scale, but actually I have a real wafer here. I cannot see myself, so I only hope that you can see it. So this is a wafer that comes out of the clean room, and it contains thousands of samples, so thousands of quantum dot arrays, which I think is quite exciting. I'm not sure if you're going to the clean room a lot, but usually, you know, we make 12 samples and then 11 don't work. So this is really nice that we have just thousands of samples in a go. And the quantum dots are formed in a 28 silicon isotopically enriched substrate, silicon MOS, so silicon and then silicon oxide, and then the gates. And here you see an SEM of the sample, where you see the gates here, and you see a lot of other material, but that's just to facilitate the chemical mechanical polishing. And if we take a cross-section of the sample, you see that we confine our electrons, first of all, with the 2-deck, and then in the second dimension by means of fins. So you see 2 fins here, and I'll talk about that later, why we have 2 fins. But we can also take a cross-section in the length, and you see our gates. We have 7 gates, and this sample could, in theory, facilitate 3 quantum dots. So the gates on top of the quantum dots are used to control the chemical potential of the quantum dots, so the number of electrons, basically. And the gates next to them are used to control the tunnel coupling between the quantum dots. We can compare this sample to a sample from IMEC, that's also, as I said, industry made. And you see that our technique, well, you can see the differences for yourself. So to see if industry samples can indeed form qubits, we need to check 3 things. First of all, can we make quantum dots and catch electrons? Secondly, can we perform single-shot readout? And then thirdly, can we control the qubit? So let's start with the quantum dots. So we do that by scanning 2 gates, gate 1 and gate 3. So we form a quantum dot under gate 2. And you see the Coulomb peak behavior that is indicative of forming quantum dots. And each Coulomb peak here represents an electron. Basically, if you lower the gate, an electron is tunneling out of the quantum dots. So we get less and less electrons. And you can see that the lines are nicely diagonal, which means, that both gates couple capacitively similar to the quantum dot, and the quantum dot is nicely in between the 2 gates, exactly where we want it to be. So we also cooled down some other samples from all over the wafer just to compare, and we got quite reproducible results. as you see here, with about the same gate voltages. So that's actually, yeah, really nice that we have high yields and kind of reproducibility. To study the behavior of our quantum dot a bit better, we can scan the plunger gate, so on top of the quantum dot, versus the two barriers, the tunnel coupling gates, such that we empty the dots more and more and more. So you see that here each line basically means an electron out of the dot until it's almost empty. And well, we can see that if we're in the multi-electron regime, as here, well, we already know that the quantum dot looks really, really nice. But if we go to the few electron regime, you see that next to our quantum dot, you see some other lines, which is indicative of spurious dots being in the vicinity of our quantum dot. And this is actually really common, or actually almost always seen in silicon MOS devices, because the gates and the quantum dots are very close to each other. And therefore, yeah, there might be defects in the oxide layer that is literally close to the quantum dot, and that might change the potential well or add an extra potential well to it. So they form spurious dots. Nevertheless, if we go to the multi-electron regime, we can also form two quantum dots. We call it a double quantum dot with a tunnel barrier in between. And here you see lines basically indicative of adding electrons to one dot. And if you go to the top, you add electrons to the other quantum dot. And what we can do is we can lower our tunnel barrier, so make G4 basically more and more positive. And starting from two clearly separated dots, also, by the way, these light points are where the chemical potential levels of your two quantum dots are similar, so the electron can tunnel back and forth between two dots. And if we make this tunnel barrier, basically if we reduce the tunnel barrier more and more, you can see that the wave functions of the electrons in the quantum dot overlap more and more, until in the end we have just one large quantum dot, as you see here, which means that we have nice tunnel coupling and controllable tunnel coupling, and this is very important for 2-qubit gates. So now let's look if we can do single shot readout. And in order to do that, for single shot readout on a qubit, we need to make a charge sensor, and we do that by making a nearby quantum dot, so nearby to our qubit dot basically, that is capacitively coupled to our quantum dot, or qubit dot basically here. And this nearby dot, it can sense capacitive changes in your qubit dot. So here we form a sensing dot in the second fin that we have. So we have a qubit dot basically and a sensing dot. And you can see that we can indeed sense the Coulomb peaks, so electrons being added to the dot, but you can also see that it's really faint. But this is maybe one of the perks of working with industry, because we had some feedback back and forth, and by changing by device scaling, basically, we improved this rather rapidly from a charge sensing signal of 5 picoampere in a couple of months by a factor of 100 to 500 picoampere. And this signal of 500 picoampere, that's large enough for us to do single shot readout. And why, I'll show you now. So how we perform single shot readout is as follows. Basically, first we find the last electron in our quantum dot, which is here. So this is the number of electrons in the quantum dot. And then we apply a magnetic field to split the spin state by the Zeeman splitting. And then we load an electron randomly in the quantum dot by pulsing to the 1 regime. And then what we do, so we load it randomly, and then we align our readout levels such that a spin down electron is lower than the Fermi energy. So the chemical potential is lower than the Fermi energy. So it's not allowed to tunnel out of the quantum dot, whereas a spin up electron is allowed to tunnel out of the quantum dot, which results in a sensor signal. So you want, as you see here. And of course, eventually a spin down electron will tunnel in. So we always end with a spin down. Then if we threshold the signal, so if we have a spin down, there will be no signal. And if we have a spin up, there will be a signal. So we can threshold this, and we basically have single shot readout by means of spin to charge conversion. So that we can use to, this readout we can use to measure T1, as you see here, at T1, and we measure at T1 of, well, our measurements actually take quite long, because we have a T1 of 1.5 seconds at 1 Tesla, which is one of the highest values ever measured in silicon MOS. So we're really happy with that. But silicon devices also have lower laying valley states, and this might be problematic for qubit measurements, as spin valley mixing can mess up the qubit state. So you can see that here, right? We have one value with spin down and spin up, and then the other value very closely with spin down and spin up. And then these states might hybridize at some point if you change the magnetic field. So what we can do is we can monitor the decay rate, so 1/T1 of our qubit versus the magnetic field. And we see a magnetic field dependence of our T1, and you also see this peak, and this peak is exactly where these states hybridize. It's the reduce in decay rate, an increase in decay rate or reduction of T1. So it's exactly where the states hybridize. And we find that this is approximately at 2.3 Tesla or 260 micron electron volts. And this is comparable to other silicon MOS devices and high enough for us to do spin measurements or to do qubit measurements. So let's do that. So the third thing we wanted to see is if we can make a qubit. In order to do that, we add a strip line to the sample. You see that here in red. And we use this strip line basically to coherently control the qubit by an oscillating magnetic field. And so we again find the last electron and load and read out as before, but now we add microwave pulses. So we let the qubit evolve around the Bloch sphere, and you see the Rabi oscillations here. So we can get Rabi oscillations up to 900 kilohertz. And then to study the coherence of the qubits, we do it by means of CPMG pulses. So basically pulse to the equator and then do pi pulses for a number of times and then pulse back up. And here you see the normalized CPMG amplitude for a various number of pi pulses. And you indeed see that if we increase the number of pi pulses, the coherence time increases, which you can see in this plot. So here we see the number of pi pulses and then the coherence time that belongs to that. And we get a coherence time of over 3.5 milliseconds with, I think, room to improvement because it doesn't saturate yet. And then finally, to study and analyze the quality of our qubit gates, we perform randomized benchmarking, and we get single qubit gate fidelity of about 99.1%, of over 99%. So in summary, despite the rigid industrial processing conditions used to fabricate our samples, the key performance indicators such as the charge sensing signal, T1, T2 star, and also the coherence time are all comparable to currently operated silicon MOS devices. And the formation of easily tunable double dots that bodes well for the implementation of 2-qubit gates in this system or in these kind of samples. And also what's rather nice is each wafer contains thousands of quantum dot arrays similar to the ones presented here, and they behave rather reproducibly. So that's really nice. And moreover, the improvement of the samples goes really rapidly, as you could see with the charge sensing signal. So with that, actually, we could conclude that silicon spin qubits are indeed compatible with the semiconductor industry. So this claim is proved. And if you want to know more, you can always check out our paper that is on the archive this year. And with that, I'd like to thank, well, of course, the whole group in Delft, mainly Tobias Greenman, with which I did these experiments, and the from Intel, Thomas Watson, Lester Lampert, and James Clark, and of course, Lieve van der Sijpen, who is here. And also all of you for your attention. So thanks.
Thank you very much. A very nice talk. And I see a question straight away from Chris Warren.
Hi, thank you for the very good talk. I had a question about the single qubit gate fidelities that you showed there at the very end. I'm a bit curious, you have such long coherence times, but your single qubit gate fidelity seems to be so small. What limits you in superconducting or in quantum dots, I guess?
It's a very good question, so thanks for the question. And it's also very nicely remarked, actually, because you're right. So the problem is, and that's also the reason that we didn't do more than 50 CPMG pulses. We had to, so we think we're basically charge noise limited. So we probably have a couple, as I said, well, as I showed before, in the few electron regime, we have more spurious dots in the vicinity of our qubit, which you can basically see as other spins that are decoherence factors. So that's the thing. Then still our coherence time is okay-ish, but we have our ESR line, so our strip line, that actually heats up our sample. So if we do, if we wait for longer than 3.5 milliseconds, our sample just heats up and we, our readout point drifts. So we basically lose our readout. And this made that we couldn't calibrate our gates really well. And therefore, we expect actually that if we can solve this issue with the heating of the sample and maybe a little less spurious dots in the vicinity, that we can get actually higher gate fidelities, because indeed there are quantum dot samples in our community that have similar coherence times, but way higher gate fidelities, such, yeah, as I said, the 3 nines. So I think it's mainly a problem of calibration and heating.
How long typically are the gates?
Yeah, good question. About, so our Rabi frequency is 900 kilohertz. So let's calculate a couple of microseconds, I guess.
Okay, great, thank you.
So I don't see other questions. Maybe I can jump in here and ask what material are the gate electrodes and the strip line? And is there any chance that the industry could provide alternative materials?
Yeah, so that's a very good question. To be honest, I don't know. That's one of the things if you work with Intel, so they have a lot of company secrets. So we know that we have a silicon substrate, which is purified, and we know the distance between the gates is 15 nanometers, so the pitch. But we're not allowed to know the materials of the gates. So usually in Delft, if we make them in Delft, we make them from aluminium or palladium, but I don't know what Intel does.
Okay, this sounds relevant for this overheating problem you're having, so.
Yeah, that I agree.
Yeah, okay.
So our feedback to them would be, okay, it is heating, maybe you should make a superconducting material, and then they decide to do that or not.
All right. When I looked at your Rabi oscillations, the contrast seemed really small. Maybe I misunderstood something.
Oh, the visibility.
Yeah.
Yeah, that's the type of readout that we do. The spin-dependent tunneling, basically, as I explained, the visibility there is really, really poor, actually. So you have a lot of what do you call this? Dark counts.
Okay.
And actually, there's another way of doing readout by making use of Pauli spin blockade, and you need 2 quantum dots, which gets way higher visibilities. So that's actually basically the new way of readout.
Okay. Other questions here? If not, I'll thank you for your talk. We are right on time, and thanks. Let's move on to the next speaker, who is Lucas Sletten. I was unable to make you co-host. I will now ask you to share your screen, Lucas. Let's see if this works.
Okay, I will try. I cannot. You've disabled screen sharing, is what it tells me.
All right. I have already messaged people who could make this chance. Okay, now I see something is happening.
Yeah, I see that as well.
Okay. Lucas and I actually happened to meet here in Göteborg 3 years ago, and since then lots of things has happened, including these nice results he'll be presenting. His talk is entitled Quantum Acoustics with Surface Acoustic Waves. So please.
Great. I'm just going to confirm you can see the right screen with just
Yes.
the slide and the laser pointer.
Yes.
Excellent. So thank you, Simone, for the invitation to talk. This has been a great conference so far, and I'm excited to see what later tonight and tomorrow brings. So my name is Lucas. I come from Connor Lander's group at JILA in Colorado. And today I'll be talking about maybe something else that's a bit exotic, but doing quantum acoustics with surface acoustic waves, kind of investigating what kind of applications surface acoustic wave technologies might have in the quantum world. So first, I'm going to say a little bit about why we're interested in sound, what's interesting about phonons. So for one, phonons interact with a really wide range of quantum systems, and this has made them attractive elements in transduction schemes. For example, the current state of the art in converting between microwave and optical photons is using a mutual coupling to a phononic, to a silicon nitride membrane, where the motion modulates 2 cavities and that lets you do conversion. These vibrational modes can have really impressive coherence times. I think you can ascribe a lot of this high Q to the fact that you can engineer the mode structure much better in phononic systems because sound can't propagate into a vacuum. And I think the thing that we're most curious about with surface acoustic waves is the fact that sound is really, really slow. So almost 1,000,000 times slower than light. And this lets you, the fact that you can deal with a slow field lets you do some pretty interesting things. I think the way to say it is sound gives you a really long delay in a really small space. And so if you want to make something like a multi-mode cavity with lots of resonant modes, that delay is much easier to make than using light. So for example, if you want to make a cavity with a long delay using microwave light, that this group, Andrew Haug's group, can fit about 1 meter of cable on a chip, and this gives them a spacing between resonant modes of about 90 megahertz. Whereas, Per Delsing's group, here at Chalmers can, in this very sub-millimeter geometry, make a resonant spacing of, 50 times smaller. And so what we're curious about is, whether this large density of resonant modes, which basically gives you this big collection of simple harmonic oscillators, has some potential use in storing and processing quantum information. And we've seen, so far in this conference that harmonic oscillators are pretty interesting candidates as qubits. So they have one dominant error, phase flips are quite rare. There's a large Hilbert space, so you can do interesting encodings, you can store more information than a bit. But doing this requires some additional nonlinearity. And so if you want to use our acoustic cavities to store information, we need to integrate them with some nonlinearity. And not surprisingly, the way we're going to do that is using a superconducting qubit. And so the kind of vision is to take a multi-mode acoustic cavity, couple that to a superconducting qubit, and make some quantum random access memory, where the information is stored in a registry of acoustic modes, and the superconducting qubit provides the nonlinearity you need to initialize, measure, and do interactions between these modes. And there's been a lot of really cool results coupling superconducting qubits to acoustic cavities, either using bulk acoustic waves or these surface acoustic waves like I'm going to talk about, and also these one-dimensional phononic cavities. So there's been a huge explosion of really cool results using these acoustic cavities. But the kind of generic thing you need for all of them is really great control over the simple harmonic oscillator's quantum state. And this generically requires both a strong interaction and low loss elements. And so in order to set some goals for what we're hoping to achieve with these early demonstrations for surface acoustic waves, I'm going to be specific exactly about what model we're going to use. And again, not surprisingly to this audience, this is going to be a Jaynes-Cummings Hamiltonian where there's an array of acoustic modes, a two-level system, and some hopping interaction where the phonons can hop into the qubit excitation and back if they're tuned on resonance. So inspired both by this proposal to build a quantum random access memory and by the great success of superconducting qubits coupled to electromagnetic resonators, we're going to operate in a dispersive regime where the qubit transition is tuned far away from the array of acoustic modes compared to its coupling strength. And in this regime, you have this A-dagger A sigma Z interaction characterized by strength chi. And again, this is familiar for most people here, but the way to think about this is your qubit frequency then acquires a number-dependent shift. So if you have a coherent state in your harmonic oscillator mode, then your qubit spectrum will split into different peaks, each corresponding to a different number of excitations, and with the weight of the number distribution, associated with the heights of the peaks. And the splitting happens when you reach the strong dispersive regime, where this interaction strength exceeds your dissipation rates, kappa and gamma of the cavity and the qubit. And so this is really going to be our goal for these early quantum acoustics devices. For one, it conclusively shows, even for a coherent state, that your harmonic oscillators are quantum, which is a prerequisite if you want to use them to store quantum information. And as we've seen some today, for the case of microwave cavities, electrical cavities, this precipitated a huge number of really exciting experiments, including the preparation measurement of arbitrary cavity states. And to make this more than an acoustic remake of a hit from 10 years ago, we're going to do this in a way that's compatible with the large number of modes in our acoustic cavities. So that's the kind of grand vision. Next, I'm going to go into more detail about exactly what surface acoustic waves are, because they're probably a little bit exotic. So these waves, particles move in ellipses, and the energy is confined to about a wavelength from the surface, and they have a few kilometers per second velocity. If the material is piezoelectric, there's a commercial developed technology around using these waves for filters and other things. And one of the core elements of this is something called the interdigitated transducer. This is just a periodic capacitor. And if you apply a voltage, that will put some strain in the piezoelectric substrate, which will then radiate away if that voltage oscillates in time. And alternatively, a wave passing underneath will apply some voltage across this capacitor, which you can measure. So this is the speaker and microphone for surface acoustic waves. If you want to make a multi-mode cavity, if you want to confine these waves, you need to make a reflector. The issue is a very high reflective element on the surface will scatter waves not only back where they came from, but also down into the bulk. And so we use a distributed array of weakly reflective elements where none of these elements scatter strongly to the bulk. And in a narrow frequency range, the incident radiation is completely reflected because each individual reflection ends coherently. Both of these elements are very frequency sensitive. You can see they have many wavelengths long, and so on a typical weak piezo like gallium arsenide used here, around 100 elements gives you about a couple percent bandwidth. The mirrors are also narrow band, but their bandwidth is determined by how reflective each element is, whereas the total reflection is set by how many elements there are. And so this is a typical reflection from one of these mirrors. So these are how you build classical acoustic structures, including cavities. You can imagine making a cavity by having two mirrors face each other. But if you want to do quantum acoustics, we need some source of nonlinearity. And we achieve that quite simply by taking one of these transducers and shunting it by a Josephson junction. This gives you an anharmonic LC oscillator. This gives you a transbond qubit, basically. You can model as a flux particle in its cosine potential. And these early, the first demonstration of quantum acoustics with surface acoustic waves was done here, again at Chalmers using a superconducting qubit coupled to propagating acoustic waves. And you could tell this is quantum by how it reflects and emits sound. So these are all the components you need to do quantum acoustics with surface acoustic waves. And now I'm going to take a step back and describe a bit of a subtle problem in that higher level vision I presented earlier, and also how surface acoustic waves are really well equipped to solve that problem. So our system is this multi-mode cavity with a superconducting qubit. The things we want a really small mode spacing. We want a lot of resonant modes. We want to be dispersive, so our qubit doesn't strongly hybridize with those modes. And at the same time, we want a large dispersive shift, which means we'd like a strong coupling. If you have a coupling that does not depend on which mode the qubit interacts with, so if you have this forest of modes and they all have the same coupling strength, you kind of walk yourself into a bad situation, because you can't tune the qubit from a resonant mode by more than half a free spectral range. And then this dispersive regime requires that either these modes are far apart or you have a small coupling. And this kind of defeats the point of wanting to have these, there's lots of modes with strong coupling. And so what you could do instead is you can take your modes which are farther away, which can tolerate a stronger coupling, and you turn that coupling right up. And that's okay so long as the modes nearby to where you'd like to, park your qubit in frequency space have a very weak coupling. This frequency sensitive coupling lets you both have a high density of modes, but without strong hybridization and with strong coupling. And it turns out IDTs are great at giving you this frequency sensitivity. And to understand that, you can take an IDT, split it in half and apply electrical impulse. That will put some strain in the substrate, which if you evolve in time while measuring the strain at this location, what you see are two pulses. You see first the pulse coming from the close IDT half, and sometime delay later you have the farther IDT half. The frequency response of this IDT is then the Fourier transform of its impulse response. And the Fourier transform of two squares with some delay between them is perfectly analogous to double slit diffraction. You get this slow sync modulated by this fast sine. And of course, you can imagine any shape in the IDT you'd like. You just take the Fourier transform, its geometry, and that will give you its frequency domain response. And crucially, this structure here with a large interaction strength right next to a weak one is exactly what we'd like to do. We'd like to put our qubit here and have it interact with acoustic modes there. So this is how we make our structure in a little cartoon. So there's our transducer split in half. Our split junction loop just makes a tunable transbond qubit. And then we use these two Bragg mirrors to confine acoustics into standing waves. This is what the device looks like as an SEM micrograph. This is false color aluminum on gallium arsenide. You can see the mirrors confining our acoustics in green. The transducer is here in purple, blue, and red. And then the junctions are in gold. Additionally, we strap this big dipole paddle so we can read out with an electromagnetic resonator. So our window into this experiment is we monitor the qubit state using readout from an electromagnetic resonator. Copper cavity, right? So the presence of these mirrors creates two different phononic environments that our qubit sees. Inside the mirror bandwidth, these modes are confined, while outside they propagate. So outside the mirror band, this IDT acts as an antenna, and it modulates the qubit's spontaneous emission rate as a function of the qubit's frequency. Whereas inside the mirror band, it modulates its interaction strength with the resonant modes. And so you can see there's this notch where the qubit does not want to talk to phonons, nearby a place where it does strongly. So to see if we really realize this with this device, we take our qubit and we tune it we tune its frequency across the resonant modes of our acoustic cavity. When we do that, you can see the qubit tune, it runs into a bunch of acoustic modes and then tunes out of the mirror bandwidth. Crucially, you can see a strong interaction, big avoided crossings in the middle, which then vanishes on the edges. And if you extract the avoided crossing strengths, what you see is large crossings in the middle of several megahertz and then weak crossings at the edges. And one thing I'd like to point out here is if you took your mirrors and moved them twice as far apart, you would have twice as many resonant modes, but you would still be able to park your qubit at this frequency and be dispersive with all of them because their interaction just becomes vanishing at this frequency. So to see if you've achieved the strong dispersive regime where we can resolve, the shift of a dispersive shift of a single phonon, we tune our qubit to this frequency. At this frequency, we can do spectroscopy. We can see its line width is a couple hundred kilohertz, and this isn't so great. But what we've made is a really fine pitch capacitor. They're 90 nanometer lines, as well as a bunch of things on a piezo. So this is actually we're happy, we're proud of this line width, even though it's not competitive. You can then drive very hard, and since there is a residual hybridization between the qubit and these modes, even though it's in the dispersive regime, if you drive 100 or 1,000 times harder, you can populate and read out the phonons. You can measure their spectroscopic line width. It's about a couple hundred kilohertz. This is really dominated by diffraction. We made a flat mirror and phonons can walk out. We've made focusing mirrors in the last year, and these really beat down the line width by over an order of magnitude. So this is really limited by diffraction. And so the experiment we'd like to do is we'd like to pump one of these phonon modes at a time. That will drive a coherent state in the mechanics in the surface acoustic of resonator. And then we'll monitor the qubit spectrum while we drive that and see if we can resolve phonons. So we'll do that first for the strongly coupled mode in the middle. And as we turn up the size of the coherent state, we see the 0 phonon qubit spectrum start to grow shoulders, which then dominate the 0 phonon line. And you can say, oh, look, I can see 0, 1, 2 phonons. You can really count them. And again, you can do this for more than one mode. You can do this for this closely but more weakly coupled mode. You can count phonons for this mode here. It's weakly coupled and far detuned, and so it doesn't quite enter this regime. But I included just to point out if the parameters are better, this would be able to be compatible with lots of different acoustic modes at the same time. And so that's where I'd like to conclude. I've shown you that we can resolve phonon number states in this multimode cavity, showing that we have the strong enough coupling with the coherent enough components. And I think an interesting thing is that being able to engineer the interaction between the qubits and the qubit and the phonons, really gives you a way to deal with the tons of acoustic modes that these acoustic cavities give you. So it's surface acoustic waves gives you not only a large number of resonant modes, but also a way to deal with that large number, with potential uses as a quantum random access memory. And with that, I'll say thanks again for your attention, and now we'll take questions.
Thank you very much for a very nice talk. Questions? Since you're on this particular slide, I was a little confused by your choice of making junctions in gold, and generally also by this false color scheme. So could you go through it once more for me?
Sure. So everything you see is aluminum and gallium arsenide. So the metal is all the colored metal is aluminum. The junctions are in a different layer. So is your question why I chose gold?
That's the one question, yes.
I think it looks nice. Is that an appropriate answer? Or
I mean,
I see. So the color is gold. It's all aluminum. So the color is
thank you.
They're
now
absolutely
it makes more sense.
aluminum oxide junctions.
That makes more sense. Thank you.
There is no normal metal anywhere in this. It's all aluminum and gallium arsenide.
And the red and the blue, they are both ground, or?
Yeah, I will, if you don't mind, go back to this picture. So red and blue are two different electrodes. They're separated. So the junction needs to shunt the red to the blue, because that's what the capacitance is between. And then the pink is just where red and blue are overlapped too finely to see in this image.
Okay, so the red at the bottom and the red in the middle, they are galvanically connected.
You can see this finger, like in the schematic here, there's a finger that passes through.
Oh yeah, okay, got it. Yeah.
Yep, so this is identical to the schematic.
Okay, thanks. I see a question from Marina. Kudra, please.
Hey, Lucas, so now if you manage to make this random access memory, and let's say you have phonons in a few of these modes, how can you then selectively use the qubit to kind of read out from these different modes?
Yeah, that's a good question. It hasn't been done, so I can speculate. What you can imagine doing is doing Wigner tomography. Using, if you're in the strong dispersive regime, deep into it, you can displace those acoustic modes one at a time, and then do Wigner tomography to read them out. And this is going to be complicated because there's lots of them, and if they have different dispersive shifts, that does not work so well. But at least it's been done by David Schuster for his quantum flute. So I think it's if you want to know the answer to this, it's the multi-phonon blockade, I think, is the way they do this with photons.
Yeah, thank you.
There's also David.
Thanks for that interesting talk. I wonder, could you also, while you're on the slide, could you comment what you said, this paddle antenna, and then you coupled to a copper cavity? Could you comment about how you get signals in and out?
Sure. I gloss over it because it's a little bit standard. So you can see this is what their actual chip looks like. You can see there's the two paddles here. It's in a copper electromagnetic waveguide cavity. So this has a resonant frequency of like 6.5 gigahertz. You shoot in microwaves to the cavity and measure its frequency, and that is dispersively shifted by the qubit. So it's the same interaction the qubit has with the acoustic modes. It's just a much stronger interaction, and we use that dispersive shift to determine its state. Did that answer your question?
This is just coupling to the qubit. I get it. Thank you.
We have one more question from JILA.
Hi, thank you for the excellent talk. About your ITT, interdigit fingers, can I ask why you have double fingers for each polarity? Like
yeah, sure. So you're asking why these electrodes are split in half. Like the electrical periodicity is half of that, half of that of the mechanical. And that's because if these fingers are done with exactly the same fabrication step as the mirrors, and you can imagine if they really had the same periodicity, then this is not only a transducer, it's also a reflector, right? This will reflect phonons in the same way the mirror does. And by splitting the IDT in half and cutting them and doubling the mechanical periodicity, you change the Bragg frequency to be twice the frequency that effectively launches sound. So you basically turn it into a lambda by 4 anti-reflective coating instead of making it the same as your mirror. Does that answer your question?
Yeah, that's great. Thank you very much.
All right, maybe I'll take the last question. Coming back to the concept of the QRAM, what control strategies you are thinking about to let this qubit talk to these multimodes? Is it parametric modulation or higher side bands or?
Yeah, so the proposal that I cited is for using like 3-way, 4-way mixing of the junction to do some parametric gates between the acoustic modes. That really requires distinct energy differences between the modes you'd like to couple to each other, and that's really not natural in a Fabry-Perot type cavity where the modes are evenly spaced. If you'd like to do that, you have to do some, you have to basically engineer a frequency-dependent delay to make your cavity mode spacings different, and we have some ideas for how to do that. So that's one thing we're thinking about. Sidebands are definitely another possibility where you both, excite a qubit and the cavity modes at the same time, and since
so yeah, please.
So it's a little bit pie in the sky at this point. So we haven't done too much, wringing our hands about how exactly we would do these gates. There's a proposal. We have some ideas for how to make that happen. I think there's some more intermediate ideas for what we could do in the meantime as well.
All right. Thank you very much for this talk today.
Yeah, thank you. I will.
And let's move to the last speaker of the session. Quentin, are you there?
Yes, hi.
Okay, so Quentin is ready to talk about high fidelity gates on fluxonium qubits. please go ahead.
Yeah. Okay. You can see everything, right? Okay, good.
Yeah, we can see it.
Okay, hi everyone. So thank you very much for the invitation, and thank you for still being here for the last talk. So my name is Quentin Ficheux. I'm a postdoc working at the University of Maryland College Park. And today I would like to share with you our most recent results on the implementation of high-fidelity gates on fluxonium qubits. So I'm a member of the Joint Quantum Institute in the group led by Malnou. So I would like to acknowledge all the members of the group. So here's a picture. All the people with the name in red here are currently working on trying to make this fluxonium circuits a good qubits for quantum computation. So the first thing I would like to do is to remind you what is a fluxonium qubit. So a fluxonium is an object which can be described by the following electrical circuits. So this circuit is made by a junction in parallel with a capacitor and an inductor. And we say that this circuit is in the fluxonium regime when we have these two following conditions. First, the value of the inductor is much greater than the inductance of the junction. And also, we make sure that the ratio of the Josephson energy to the charging energy is between 1 and 10. So for realistic values of these parameters that satisfy these two conditions, and if we apply half of a flux quanta in the loop defined by the junction and the inductor, we find that the quantum mechanical behavior of the circuit is equivalent to the one of a massive particle evolving in a double well potential. So we can solve this problem, and we find that the first wave function of these circuits are the symmetric and anti-symmetric superposition of the particle being localized in the left and right wells. So first of all, you see on this picture that these two states are very close in frequency. They are very close in energy, which means that the transition frequency is typically less than 1 gigahertz with these parameters, which means that that's about 1 order of magnitude smaller than the one of typical superconducting circuits. And so the way we like to understand these circuits is by having a look at the transition dipoles between its states as a function of frequency. So let's have a look at the charge operator, at the matrix element of the charge operator. So if we have a look at the matrix element of the charge operator between state I and J, we find that the qubit transition here at 160 megahertz has a relatively small matrix element. So the value of this matrix element is crucial as it determines two things if you want to use this 0 and 1 state as a qubit. The first one is that if you want to drive at this frequency, the driving Hamiltonian is proportional to the charge operator, which means that if you want to, which means that the Rabi frequency or the speed of any quantum logic that you want to implement at this frequency is going to be proportional to the drive amplitude and to the value of this matrix element. And at the same time, our circuits are limited by dielectric losses due to material imperfection, which means that the energy relaxation rate from state 1 to 0 is also controlled by the same matrix element but squared. So this is the value of this matrix element is very important in our qubits. The second thing that you observe in this diagram is that this is a highly anharmonic circuit, which means that the ratio of frequency between frequency of 0 to 1 to 1 to 2 is about 30. So even if you drive this transition very fast, this is really a true qubit in the sense that you can completely neglect a possible excitation to the second excited state. And also, as you will see, we can use this 1-2 transition to mediate interaction between qubits, and we typically use the 0-3 transition to create a non-zero dispersive shift between this qubit transition and a readout mode around 7 gigahertz. So let me show you what this circuit looks like in practice. So this is a very standard circuit. So it's just an aluminum circuit deposited on either a silicon or a sapphire substrate. So the circuit is made of an antenna whose geometry determines the charging energy EC. In the middle of this antenna, there's a loop in which there's a small junction here whose area is proportional to EJ, and which is shunted by a few hundreds of Josephson junction. And they provide an inductance in the range of a few nanohenry, a few hundreds of nanohenry. So this circuit here is embedded in a 3D cavity We use a copper cavity at 7.5 gigahertz that we use to perform readout of the qubit. So if you want to know if it's a good qubit to store quantum information, you may wonder what's the coherence time of this object. So we took this qubit and we measured the coherence time of this qubit, and here is what we got. So this is a Ramsey experiment here, and we found that the Ramsey signal is the one we usually observe. So it's a cosine with a decaying exponential with a coherence time which is 1.16 milliseconds. So T2 star is 1.60 milliseconds. It's really like in a Ramsey experiment. It's not a CPMG coherence time here. And so we were pretty excited with that because this was the longest Ramsey fringe that we had ever seen. And for super qubits, that's one of the most coherent qubit out there. So, and this is not really surprising if you take into account that T1 is also 1.2 milliseconds. So if you have this T1 and a good thermalization, you expect that you can achieve this kind of value for T2. So what I want to stress here is that this coherence time is actually quite stable, which means that this Ramsey fringes that I was showing is actually average over 12 hours. And if you just have a look at the individual points, you find that the coherence time is always above a millisecond over a 12 hours period. So it's really this is really robust. And it's possible to just average for so long because the qubit frequency is stable within 100 Hertz. And again, it's not surprising because this matrix element was controlling this energy relaxation time and led to this increase in T1. But you may wonder, is that a problem to implement quantum logic, and can you make efficient gates on this qubit? So to prove that this is a viable route, we implemented single qubit gates, and we could benchmark single qubit gates using randomized benchmarking. So for those who don't really remember it, randomized benchmarking consists of applying a list of Clifford operation. So n Clifford operation before undoing them, and we have a look at our ability to undo them as a function of the number of operations that we did. And we find that we can do several thousands of operations, which correspond to a gate fidelity of exceeding 4 nines, an average gate fidelity of exceeding 4 nines. So this is indeed a very good qubit, and actually we know that this is right now limited. We understand that now it's really limited by the coupling to the input pin, and we are pretty confident that we're going to get this number up by close to 1 order of magnitude relatively soon. So this is for single qubit gates. So, but you may wonder, what about 2 qubit gates? Well, so then the question becomes more difficult. So if you have 2 qubit, a red and a blue qubit, you have 4 computational subspace. How do you implement a 2 qubit operation? Well, it's not easy. So we tried several possible options to determine which gate implementation is the one working best. And so we have like 4 gates that we did so far. So other groups are also investigating other kinds of gates. And so in this talk, I will just describe the first gate that we did. So the first 2 gates that we did are using the second excited state to make qubits interact. But then we investigated other qubits that stay in the computational subspace. So our initial idea was to say these qubits are very slow, they have a low frequency, so they will also interact slowly. So it's hard to make an interaction. So if you zoom out from these hundreds of megahertz manifold, and you have a look 5 gigahertz above, you have these 2 states up there. And these 2 states can be interacting. So the idea was to say that if we can take the population from state 10 and 11 and bring it up to the state 20 and 21, and then back down, then we will accumulate a phase on state 10 and 11, which can result in a CZ gate. And if these 2 oscillations are synchronized, at the end of the gate, there will be no leakage in the 20 and 21 states. So how does it work in practice? So in practice, we just copy paste the design that I showed you earlier. So now we have 2 qubits on the same chip. these 2 qubits have an antenna, so they experience a dipole-dipole coupling. And so this dipole-dipole coupling can be modeled as a shared, as a mutual capacitance. So what this capacitance does, it almost does not create interaction within the computational subspace, but it's actually creating a level splitting between the 2-1 and the 1-2 states around 5 gigahertz. And this level splitting is quantified by the energy scale delta. In our case, it's about 1/45 nanosecond. So this, so if we want to identify all these transitions, what we typically do is that we perform spectroscopy of this 2-qubit device as a function of the external applied magnetic flux, which is the flux through the 2 loops. So it's a common flux in the 2 fluxing loops. And then what we observe is that we can see this 2-qubit transition here at very low frequency. So down there are 72 megahertz and 136 megahertz. Which means that we can directly drive them using an FPGA board. We don't need to upconvert using a radio frequency generator. So the gate implementation is pretty simple. And if we scan 5 gigahertz above, we find that we can identify all the transition to higher states, and in particular this orange transition here and the blue transition, which are the one interesting for us because they correspond to the transition 1020 and 1121. So if we want to implement this gate in practice, we have 2 tuning knobs. So we want to just use one single microwave generator to do a synchronized cycling of these 2 transitions. So the 2 tuning knobs are the frequency of the drive and the amplitude of the drive. So first of all, we drive at a frequency in between these 2 transitions, between the transition 1020 and 1121, so as to synchronize the 2 transitions. So that at the end of the gate, the population comes back to the computational subspace. So if this condition is met, we can think of the trajectory of the quantum state in terms of a Bloch sphere between the 1020 state and 11 and 21 states. So in this Bloch sphere, the quantum state is following a closed trajectory, and it's coming back to the 10 and 11 state. The other tuning knob that we have is the drive amplitude. So if we want to accumulate a phase difference equal to pi to implement a CZ gate between this 11 and 10 state, we have to adjust the drive amplitude so that the phase difference, which is determined by the solid angle of this trajectory in the 2 blocks here, corresponds to a phase difference of pi. And it turns out that for a drive amplitude that corresponds to a gate duration of 1/delta, so about 45 nanoseconds, we accumulate a phase difference of pi with our system. So in that case, we implement the unitary 1 EI510, 1 EI511. And with a Z rotation, we can just come back to a CZ gate 111 -1. So how good is this gate? So again, we can perform a randomized benchmarking of these 2-qubit gate. So we can implement a list of 2-qubit Clifford operation and see the decay, the function of the Clifford number in blue. And if we interleave the CZ in between each Clifford operation, we get the yellow curve. And we can actually interleave 2 CZ, so CZ squared if you want. Then we get the green curve. And then we can interleave 3 CZ and get the red curve, and so on and so forth. And what we can plot then is the fidelity of CZ to the n as a function of the number of interleaved CZ gate. So what we could find is that if we just interleave 1 CZ gate, we benchmark a single CZ gate, and the fidelity of a CZ gate is 99.2%. So we are very happy with that because it's already a relatively high fidelity. At the same time, as we benchmark CZ to the n, we find that the error rate grows linearly, which is a signature of the fact that the error is due to incoherent processes. In our case, it's limited by the coherence of the second excited state. And the gate duration is just given by delta. So it's slightly longer because in practice, the gate has finite edges. but it's not tied to the qubit frequency. So we can just get a very fast gate. This is actually one of the fastest microwave activity gates on superconducting circuits right now. So this was our first attempt on making a 2-qubit gate, and we can compare it to other gates available in the field. And it turns out that our gate result is relatively comparable to what other people have. The gate error is still a little bit higher than flux activated gates, but we know how to make the two states a lot more coherent now. So we think that this error rate will very soon drop by about 1 order of magnitude, and it will be comparable to results available in other platforms such as ions. So, so with that, I would like to thank you for your attention and to conclude by saying that I hope I convinced you that it's not so much an exotic talk, but fluxonium is actually a viable option to implement quantum computing. Thank you.
Thank you for a very interesting talk. Floor is open for questions. While people think, I'll ask a technical question. You mentioned this dipole coupling and dipole-dipole coupling that enables interaction. I was wondering what considerations are important. Does the outside cavity play a big role? And would you like to make this coupling big or small?
Yeah, right. So this is just a regular capacitive coupling between 2 qubits. So that's just similar to what can be achieved between capacitively coupled transmon. So it's entirely determined by the relative position of the two antenna, and the capacitance value that we have is comparable to the one that people typically use with transmon. So
yeah, it seems like you don't want to make it very big. Is there a reason why?
No, actually, we didn't do any parameter matching to achieve this 2-qubit gate. So if we could make it bigger, in that case, that would just increase the energy splitting here, and that would make the gate faster.
Yeah, that was I was wondering. So it hasn't been optimized in any way.
No. There's no parameter matching so far. It's our first try for a 2-qubit gate.
Very nice. So I see Per Delsing.
Yes, thank you for a very nice talk. Very impressive data. So I wonder, have you measured the excited state population of the qubit?
No, actually. We have a single shot readout in the computational subspace, but we don't resolve the blobs of the second excited state, if that's the question.
Okay.
And if the question is what is the temperature of this state, actually that's very, as far as we know, it seems to be very similar to the one of a transmon. So it's really a transmon-like transition at 5 GHz. So that's it has a few % of excitation probability.
So you've shown very competitive numbers for the gate fidelities and of course the coherence. So if you think about scalability, how do you see this fluxonium as compared to transmon?
Right now, it seems that I'm not a scalability expert, but it seems that it's compatible with a transmon-based scaling architecture, I would say. So you can just reuse. You can just adapt the size of the antenna of a transmon so as to get an EC of about 1 GHz, not 0.3 GHz, which is typical of a transmon, and then you just have to replace the small junction by a junction shunted by a loop with this array of junction, and that's pretty much it. Now on the control side, now the qubit frequencies are lower, which means that we typically don't use RF generator. We either use directly the output of an AWG or FPGA, but that's pretty much the same cables and same everything else.
Okay, thanks. Still last chance to ask a question if you wish. If not, I'd like to thank you for your talk. And I'd like to thank at this point, this is the last talk of the session, so I'd like to thank all the speakers of the session for their contributions. You've all presented very nice experiments at the state of the art, and it was a great pleasure for me to chair this session. So I'll thank everybody also for listening. And our workshop continues tomorrow. We start again at 2 p.m. Central European time, and there will be a talk of our keynote speaker, Will Oliver. So whether it's morning or afternoon or evening, I wish you a good continuation, and I'll see you tomorrow.